Hello, my name is Brian Murray. I am a PhD candidate at the University of Tromsø, the Arctic University of Norway. The title of my presentation today is Deep Representation Learning Based Vessel Trajectory Clustering for Situation Awareness in Ship Navigation. My supervisor is Luku Prasad Pereira, who is an associate professor at the University of Tromsø, who has also contributed to this work. The outline of today's presentation is as follows. I'll start out with a short introduction and tell you a bit about historical AIS data as well as trajectory clustering. And after that, I'll discuss the methodology of the study, where I'll present the autoencoder and tell you a bit about recurrent neural networks. Then I'll tell you a bit about recurrent autoencoder structures, as well as the beta variational recurrent autoencoder that were utilized in this study. After that, I will present some of the results from the case study that we conducted, where I will present results of the latent representations that were generated to represent trajectories in the historical data set. After that, I'll show you some of the results of what was done to cluster these representations, and then the resultant trajectory clusters. After that, I'll have some concluding remarks on the study before presenting some further work that has been done, and finally we will end with questions. So historical AIS data yields a lot of information about maritime traffic. Now AIS, or the Automatic Identification System, is a system that's installed on all larger vessels, which relays ship information such as the position, the course over ground, speed over ground to other vessels in the area, originally intended to aid in collision avoidance, such that navigators are able to gain a better degree of situation awareness. These data are also transmitted to shore-based receivers as well as to satellites. And all of this data is actually stored in historical AIS databases that allow us to gain a lot of insight into the historical behavior for a given region. So for instance, here we see on the right-hand side, we have an image of a heat map surrounding the city of Tromsø, Norway, where you can then see various regions where there is more traffic than others. Now, in this study, what we'd like to do is present a method to utilize deep learning to facilitate trajectory clustering. So by trajectory clustering, what we mean is that we would like to take all of the historical data, for instance, as seen here on the heat map on the left, and generate unique clusters of ship behavior. So this could, for instance, relate to different routes where vessels have a certain behavior that can be characterized as normal. And based on these clusters, we can then get a better insight into the traffic in the region. So if we're able to discover these clusters of trajectories, these can then be used to model the normal traffic in the specific region. And this could be then used for subsequent anomaly detection, conducting trajectory predictions, as well as path planning, collision avoidance, and as well as a general maritime situation awareness. So such applications can provide a basis for decision support for operators in vessel traffic service centers, as well as to navigators on board conventional vessels, in addition to providing a basis for maritime situation awareness to future autonomous vessels. I will now present the methodology of this study, and overall, the methodology can be viewed in two parts. The first part is generating low-dimensional fixed-size representations of the historical AIS trajectories using deep learning, and the second is then clustering these representations using standard techniques. So the idea here is that we have a large set of historical trajectories representing the behavior for a given region. Here we see a region surrounding the city of Tromsø as a heat map. And what we then like to do is actually generate a fixed size vector representation of every single trajectory in the data set. So we have trajectories that are multivariate time series that can have any number of lengths. We have trajectories that are 3 hours long, some that are 45 minutes long, and all of these need to be compressed into a fixed size vector. Now we need to have this vector representation in order to facilitate effective clustering. So each data point that we can actually see here in these figures is a trajectory. So here what we'll do is we'll actually investigate two different deep learning techniques, one with a recurrent autoencoder architecture and the other with a variational recurrent autoencoder, to compress the trajectories into a fixed size representation. Then using these representations, we will cluster the historical trajectories into unique groupings. A common method to compress data or to generate lower dimensional representations of data is an autoencoder structure. Now, an autoencoder can, in essence, be separated into two parts. One, an encoder side that compresses the data or encodes it, and the other, a decoder side that then decompresses or decodes the data. So on the left-hand side of this figure, we actually see the encoder in green, where the input space X here is then compressed into a lower dimensional representation H. Then the input is reconstructed from the lower dimensional representation in X hat here, which is then the reconstructed data. Now, if you train a network in this manner, what happens is that the network is able to optimize such that the mutual information between the input and the hidden representation is maximized. So in essence, what you're trying to do here is retain the most important information in the data set so that you can reconstruct it with the least loss. Recurrent neural networks are ideal for dealing with time series data and have therefore been investigated for use in this study. The idea of a recurrent network is that you actually have a RNN cell that can be thought of as some mathematical function that takes the current input xt as well as a hidden state, here denoted as ht-1, and conducts some operation on these two inputs and produces the current hidden state ht. So what's done here is that the network is able to identify relevant information from the past that is remembered in this hidden state H, as well as what's relevant to bring further in the current state xt. So the hidden state H is then passed to the next cell, which then also takes input from the next state. So here, for instance, X would be a time series representing the trajectory for a given vessel, where each X would then contain the position data, as well as the speed over ground and course over ground data. So what happens here is that the network, in essence, compresses the trajectories into a latent state that can be used further on in the network. One type of recurrent neural network is the gated recurrent unit, or GRU, which is related to the LSTM, or long-term short-term memory. And these type of gated architectures actually allow the network to remember long-term dependencies in the data that in standard or vanilla recurrent neural networks end up disappearing. So in this type of architecture, you actually have gates that can either allow or restrict the flow of information further down into the network, so it actually is able to learn what information is most important to retain and what is more important to discard with respect to achieving a goal. So here we actually see a number of gates, such as the reset and update gates, that regulate the flow of information in the network. So what you can actually do is combine the architecture of a recurrent neural network with an autoencoder structure. So here on the left-hand side, what you see is actually a recurrent encoder. So basically each of these green blocks is a gated recurrent unit. And what you can then do is you can actually compress an entire trajectory by running it through the encoder block here, and then compressing it to a fixed size vector representation, here denoted as HL. What is then done is that you reconstruct the input trajectory using the decoder, here in orange. So it takes this latent representation, or this H here, and then tries to decode the entire trajectory from that vector. So in essence, all of the information to be able to reconstruct the input trajectory has to be stored in this vector. So the deep learning architecture will then learn how to optimally store the information here such that you have as much information as possible stored in this latent representation here. A beta variational recurrent autoencoder is also investigated in this study to generate representations. And in this architecture, what we do is combine the recurrent autoencoder structure with a variational autoencoder structure. So in the same manner as previously, we have an encoder in green here that compresses the trajectory to a hidden representation, and we have a decoder in orange that takes a hidden representation and then tries to reconstruct the input trajectory. What we do in a variational autoencoder, however, is that we utilize a latent variable z that is in the center of the architecture. So what is done here is that you actually utilize a fully connected layer to estimate a mean and standard deviation of a normal distribution, and the idea is to then sample the latent variable z from this distribution. However, to be able to backpropagate through the network, we utilize the reparametrization trick, where you actually estimate z as the mean plus the standard deviation times some epsilon value here, where this epsilon is then just sampled from some noise vector. So in this case, you can actually backpropagate directly through the network without sampling from a distribution, because you can't backpropagate through such a sampling. Further, we assume that the latent variable z is normally distributed with a mean of 0 and a covariance corresponding to the identity matrix. So in the recurrent autoencoder architecture, we utilize the mean squared error as the loss function. So basically it's just the reconstruction loss, where you're trying to recreate the input as best as possible. In this case, however, we see the loss function defined as j here, which is a variational lower bound that we try to maximize. So what we see here actually is the first term is defined as log of p of x given z. So this is actually the reconstruction. What you're trying to do is reconstruct x given z. And we can actually evaluate this by using the reconstruction loss and do this the same way as we have previously, evaluating this using the mean squared error. The second term is the Kolbach-Leibler divergence between the estimated z parameter approximated by this q phi. So what you're saying here is that we're trying to get the Kolbach-Leibler divergence between the z parameter and the prior, which is actually just a unit Gaussian. So what you're actually trying to do here is you're trying to enforce the latent variable z to be a Gaussian distribution that is just basically a unit Gaussian. So here we'll get more compact distributions of the data that should be easier to cluster. The beta parameter here actually just enforces an extra weighting of this Kolbach-Leibler divergence term. So here by increasing the beta, you're increasing the regularization term itself. You're sort of regularizing it more to be more of this Gaussian type of shape. I will now present the results of a case study where we investigated a region surrounding the city of Tromsø, Norway. So here we see the results of the representation generation phase, where we've utilized both a recurrent autoencoder and beta variational recurrent autoencoder structure. On the left-hand side, we'll see the recurrent autoencoder, where what has been done is that the autoencoder structure has been trained using all available data in the historical data set. And then what we do is we run a forward pass of the encoder, so that is to say this green block. Running a forward pass of all the available data will then generate fixed size representations of each trajectory. So that's actually what's visualized in the lower figure, where each dot is actually a compressed trajectory. So what we see is that the autoencoder has been able to learn to group similar trajectories together such that it can more optimally reconstruct them. So the idea here is that if two trajectories are similar, then they will be closer together in this space, and the decoder will then see that more similar trajectories will have a more similar representation in this subspace. On the right-hand side, we see the beta variational recurrent autoencoder that has been trained in the same manner. Here, however, we utilize the representation in the Z space, so this latent space here. And what we can actually see is that given that it's being encouraged to have a unit Gaussian shape, we see that we have more compact clusters that are discovered by the beta variational recurrent autoencoder compared to the recurrent autoencoder. So it appears that the beta variational recurrent autoencoder is more powerful in generating representations where we have more compact groupings of the data that should be a much better foundation for a subsequent clustering algorithm. So here we actually can see the natural clustering that is generated by using these architectures. So what can then be done is that we apply a clustering algorithm of choice to these representations. So instead of clustering the trajectories in their original space, what we do is we compress them to these representations that are learned via deep learning, and we can then have a more optimal representation that is more ideal for clustering. So in this case, what we have done is that we've utilized the hierarchical density-based clustering of applications with noise algorithm, which is ideal for clusters of various densities and shape. We won't go into details on this algorithm, but please see this paper for more details. And what has been discovered here is that we've been able to identify unique groupings of data quite successfully using this algorithm. Again, we can see that it appears that the beta variational recurrent autoencoder has been more successful in generating representations of the data that result in more compact clusters and appear to be more meaningful as a result. So here we see the results of the trajectory clustering. On the right-hand side, we see a figure that illustrates a subset of the discovered clusters using the beta variational recurrent autoencoder. So each of the data points in the left-hand figure here actually correspond to one of the trajectories in the right-hand figure. So it appears here that the clustering algorithm was successful in discovering unique ship behavior that appears to be meaningful in this case. So again, we saw that the beta variational recurrent autoencoder had better performance in discovering more compact groupings of clusters, and we have now discovered also that these clusters are in fact meaningful in the physical domain. So this case study has indicated that deep representation learning can provide powerful representations of AIS trajectory data, and that recurrent architectures can provide fixed size representations that are conducive with standard clustering techniques. We've compared the recurrent autoencoder and beta variational recurrent autoencoder, and it was discovered that the beta variational recurrent autoencoder result in more compact clusters. Furthermore, we have found that these clusters are in fact meaningful and correspond to trajectory clusters of similar behavior. In further work, we've also looked into utilizing such trajectory clusters and data-driven trajectory prediction techniques, where the idea is to infer the future trajectory of a selected vessel based on the historical behavior of other vessels in the same region, and in this manner predict potential future collision risk. So if one is able to do this at a stage where there is no conflict, so if we see on the figure on the right, there's a non-conflict stage and a conflict stage, you can then predict the future 30-minute trajectory as visualized on the left-hand figure and be able to identify whether or not there is a risk of a close encounter situation. So at this point, you're not required to adhere to the call regs because there is no collision risk at this point. But if you're able to conduct a long-term prediction, a 30-minute prediction into the future, then you can conduct some minor course or speed alterations such that there will be no collision risk in the future. So in this manner, you're still adhering to the call regs as there is no collision risk at that point, and you're able to prevent such a situation from arising. So utilizing a similar clustering technique to that outlined in this study, we clustered the historical behavior for a given region, And on the left-hand side, we see 3 of the clusters that were discovered. On the right-hand side, you see the past trajectory of a vessel in orange here, and this trajectory was then classified to a number of the clusters that were discovered by the algorithm. And here it discovered that the most likely clusters were these blue and red clusters. And for each cluster discovered, a local prediction algorithm predicts the future trajectory for that mode of behavior. So here we have 2 trajectory predictions, which both were rather successful. So this has now been submitted to a journal in preprint form. Thank you for your attention, and we will now open for any questions.